Okay, good morning. I would like to remind you what you did the last time about the hyperplan. I defined that when you have H like this, hyperplan you have E. First of all, is the Banach state. Is a Banach space, first of all. We define the hyperplane like this. It contains the element of E, such that you have f of x is equal to alpha. And I told you that this hyperplane is right like the equation is like this form. It's the same. We call it the hyperplane. Hyperplane. We call it so. And I tell you that when E is finite dimensional, like if the dimensional of E is equal to n, the dimension of H is exactly n minus 1. That means that the codimension of E must be equal to 1. So we prove that one of the main properties concerning the hyperplane is that when H is, first of all, calculated equal 1, when H is closed, then F is continuous. We proved it just last time. If H is closed, then F is continuous, then F is continuous, H is closed. That means that H is closed is equivalent to the fact that F is continuous. And for the proof, we started by the proof of this one. We suppose that F is continuous. Let us prove this distance first of all. F is continuous. If we suppose that F is continuous, that means that the inverse image of this singleton, which is exactly equal to H, your hyperplane, this one, is equal to is closed. Because the singleton in Hausdorff topological space is necessarily closed. Because here alpha is the element of R, which is the Hausdorff topological space. Then it's closed, then the inverse image of closed subset is necessarily closed. So then if F is continuous, necessarily H is closed. It's very simple. Now we suppose that H is closed, and then we prove that F is continuous. It's not easy to choose. Let's not suppose that H is closed. If your H is closed, that means that the complement of H is open. By the definition, the complement is open, something like that. Then, if you suppose you take x0 in an element of H is C, the result R such that the ball of center x0 is contained in H is C, something like that. Very simple. But the definition of the open set with this kind of topology, of this kind of functions. Then you prove that if you remember, we prove that for all F, but first of all, if this one is an element of EC, that means that f of x0 is less than alpha, or f of x0 is bigger than alpha, because x0 is the element of the complement of H. Then you have this condition. Let us suppose this. Let's consider this first of all. We suppose that f of x0 is like this, is less than alpha. Then we will prove that for all x which we take in the ball of the center x0, f of x is necessarily also equal to alpha. That is the big property, this one. It's not easy. We suppose that it's true at the point x0, then you put on in the whole ball of center x0 and the radius r. What you are going to prove. Why you have this one is suppose that is not true. Suppose that is not true. That means that you suppose that there exists S1 in the ball such that the f of S1 is not necessarily less than alpha. Then it's not bigger or equal to alpha because this one S1 in the ball is contained in the complement of H here. Although remember, then it's necessary at this form. So we suppose that this one is true. Then there exists a point such that you have this kind of condition. When you suppose, when you put st like this, 1 over t, 1 minus t, x0 plus t, x1. This element, this one is necessary element of this ball. Very simply to prove, because S1, X0, S1 is the element of the ball, you can put the same thing for this one. For all t, you can take for all t in this closed interval, this one. For all t, you can put it for X0 here in the ball, you can put this one is a ball. But then, if you take for t, which is equal to f of x1 minus alpha, and f of x1 minus f of x0, and you compute it, you see that f of xt is necessarily equal to alpha. What is the contradiction? Because S1, St is the element of the ball, f of ft cannot be equal to alpha. Then what you suppose here is not false, is not correct. Then for all x in your ball, this one, you have necessary f of x is greater than alpha. So you use it to complete, to prove that the f is continuous. If you have this one, if S is the ball, the fact that F in this ball, we know already that this ball is equal to x0 plus r b 1 of 0 like this. Which one? The winning ball. This one. When you consider this one, if x is here, this ball can be right like this. Very simple to prove. Then you use this fact to prove that the f is continuous. You to this fact, then to this fact to prove that f is continuous. Now let us suppose that this one of f of x is exactly f of x0 from rz. When z is the element of the unit ball, you have this one. And from this condition, we can write any element s like this, at this form. Then that means that you have f of x0 plus r f of z. This one, because f is linear, f is linear. Then this one is true for any element of this ball. So f is like this. But now let us suppose the norm now. The norm of this kind of function. When I take the norm of this, first of all, this one, that means that you have f of z can be right like 1 over r of f of x minus f of 0. Something like that, this kind of thing. And when we take the supremum of the norm of f of z, when you suppose that in the unit ball like this, we see that this one might be less than one stroke of air or for some things. That means that this one is exactly the norm, what you define already, norm of F, which is not necessarily less than some. When you say, you put that when the function, which is linear, is bounded in the unit element, you prove that the F is continuous, and then F is continuous. F is continuous because this F, which is linear, also is bounded in the unique element, the unit part of this kind of function. Okay, thank you. So when you have H, the hyperplane is closed, if only if you have F is also continuous. So I'll give you some definition now before introducing the two theorem, the two geometric form of Banach theorem. First of all, the first definition I'll remind you. First of all, we suppose that A and B two convex subset, if you want, of P. It's like that, this kind of FLD. We say that the map this linear map separates. Let us consider this one. I want to be more clear. This one. We say that this one, when you consider F is a linear map, is equal to alpha. This one separate A and B. That means that what? If you have F for X is less than alpha for all S and B, and F of X is greater than alpha for all X in B. Then we say that with the hyperplane, this one separate the two convex states A and B when you have this kind of condition. And I'll give you also another definition concerning the separate. Not the fact concerning this part of course. This one means what? That means that you have, if you have your hyperplane like this, suppose that H like this. If I say that this hyperplane separate the two convex, that means that the convex like this. This convex like this. It's possible that the convex can meet the hyperplane because you have F of S is less or equal than alpha, and the same is a greater or equal alpha. Then the subset A and B can touch your hyperplane. Yeah, this condition. Now I'll give you for the following video. I'll give you the definition of two convex also, where necessarily the two convex separate strictly our two convex will be found. Okay, thanks.